It's really great to be here. I'm Rodger Hosking, formerly of Pentech, and now a part of Mercury, and we're very proud to be there since May of 2021. So we're doing great. We're doing the same kinds of innovation and products that we've always been doing, and pushing that technology curve forward. Today, I want to talk a little bit about a new term that you may have heard called direct RF. And we're going to talk about what does it mean, what's the impact, and why is it very essential that the interfaces that direct RF implies are being met by VITA standards that we've been talking about, so far in this conference. They're really important and directly related to direct RF. Okay. So this slide shows what our military is faced with in terms of problems and applications and things that they need to do to perform. Bandwidths are getting higher everywhere. People are trying to use fewer numbers of antennas on platforms to make those platforms simpler. People are moving acquisition of sensor signals to the edge, where they want to acquire the signals at the edge, digitize them, and then send them on after digitization over optical cables instead of coaxial RF cables. The signals are getting more complicated. They're getting more complicated so they can do more. They can retrieve more information from a target, for example. We're very interested in lowering the acquisition latency, the time it takes to receive a signal and turn it around. Extremely important for countermeasures. Phased array antennas are becoming very, very popular because they allow you to do in a two-dimensional planar array to acquire signals from any direction with great sensitivity in a determined direction where you want to receive and transmit to a particular target. Heterogeneous computing, where we're now introducing AI requirements, are becoming more and more important. And we're going to see more of that too coming up in the future. And then the ability to what we call stare at a very wide bandwidth instead of sweeping across it, being able to look at everything in case something pops up and goes away. If you're not looking at it, you might miss it. So that's called a stare capability. So let's see a little bit about the underpinnings of the architectures that have been around for a long time. And the first architecture I'm going to show you is called a heterodyne architecture, which has been around essentially for 100 years, doing the same kind of signal processing, but of course now we're digitizing at the end instead of having an analog detector like a FM detector or AM detector. So what happens is you start with a high RF frequency, you do a frequency translation using a mixer and a local oscillator in analog circuitry down to a lower frequency called the intermediate frequency or IF frequency, which then can be filtered and digitized now by an A to D converter called an IF ADC. And this has been around, we've been doing this for decades. So the new thing about direct RF is to try to eliminate the two different products that were required, the analog RF down converter section, and then the sampling section or the digitizer section, typically two different products. Direct RF architecture uses the fact that you can now digitize a much higher frequencies than you could before. So instead of having to do down conversion, you can directly sample the RF signal frequency. And you eliminate then the front-end RF mixers and local oscillators, greatly simplifying the size, weight, power, cost, complexity of the receiver itself. Okay, so let's take a little look then at principles of what we're doing. I'm not going to spend a lot of time here, just a quick background. And I want to talk to you about a really great guy. Tells you how the sampling process, which is taking discrete samples of an analog waveform, turning them into digital numbers so that computers can work on them. The guy's name is Harry Nyquist, okay? Born in 1889. He joined AT&T in 2017, and he immediately went to work trying to figure out how to make telegraphs faster, okay? The problem was how fast can a telegraph signal get sent across a channel? Well, he figured out that it was limited by the rate of bits that are going across a telegraph channel, limited by the bandwidth of the channel, such that the bandwidth of that channel has to be twice the bit rate going across. Now that principle has been proven and used as the basis for all of our sample data theory going forward. He was a brilliant guy. He retired in 1954 after AT&T became Bell Labs, and his contribution is enormous. So what we're doing now is we're using data converters, A to Ds and D to As, to do that sampling, but the same principles that he defined apply to those devices. So real quick, I'm going to give you a shorthand way of trying to figure out how does that apply. We introduced this back in the early 90s as a convenient way. You take fan-fold computer paper, if any of you can remember what that is, and you plot the frequency of the input signal that you're trying to digitize on that fan-fold paper with the frequency axis scaled the way I've shown here. And each of those different pages represents a Nyquist zone. After sampling, those Nyquist zones fold or collapse upon each other. What you have to do this correctly is you have to make sure that the signals that you want only fall in one Nyquist zone. What you've got to do then is get rid of all the signals in any other zone. And that's just the key and the secret. You do that typically if the first Nyquist zone with a low-pass filter, and if you do that after you sample, you're going to be able to retrieve all those signals in the first Nyquist zone. You could do the same thing with the other zones, but that's enough for now. So let's just take a look at what that sampling rate, a very high sampling rate, implies. I showed a sampling rate of 64 gigasamples per second. That's a lot. What does that mean in terms of bytes per second? That means, if you do the math, that one single channel at that rate generates 80 gigabytes per second of data. Now, how does that compare with the typical interfaces that we deal with in embedded systems? Well, it's pretty significant. You can see that a PCIe Gen 4 by 16 will give you 32 gigabytes per second, which is really pretty good. And that is a very fast, advanced interface. So there's a problem that DirectRF poses to solve, and that is, how the heck do I get all those samples into my system, through my system, to anything? Even how do I get them into an FPGA, which is the traditional way of solving the problem? Well, there's a lot of different solutions. Many of these RF ADCs have built-in digital down converters as part of them, so that they can tune into a narrow slice of that input spectrum and then use a lower rate to deliver that slice. But that doesn't give you the full stair bandwidth going forward. It reduces it. For some applications, it's exactly what you want. But in other applications, you want to get as much of that instantaneous bandwidth that you've digitized as possible. So we're going to talk a little bit about how that's done and some of the devices that have come out to make that possible. What we're trying to build typically, or as a good example, would be an RF transceiver system, something that you might find in a radar, where you've got an RF A to D converter, direct RF front end, and you've got a direct RF back end for the transmit side. And the same principles that work on the front ADC side apply to the DAC side on the output. You have the same Nyquist criteria that you have to supply. But this architecture is really very important for phased array antennas, because you have a lot of different elements. You might have hundreds or thousands of elements. Each of those elements typically needs a transmit and a receive channel. And getting rid of all of those analog RF circuits that were there before now makes a high channel count phased array antenna much easier to do to cover very wide bandwidths with very fast tuning and hopping between frequencies and doing the beamforming necessary to capture the signals that you want to capture. So a major idea of how do we build systems going forward, a new architecture, has been enabled by this direct RF concept. One of the first chips that really implemented this very well, this is a chip, the RF SoC, which is basically a Xilinx now AMD chip, was able to digitize at 5 gigasamples per second. That gave you about a 2 gigahertz instantaneous bandwidth, and it did so with 8 channels of ADCs, 8 channels of DACs, okay, so it's a transceiver, powerful FPGA fabric, and then powerful interfaces to the outside world over 200 gigabit, there were 200 gigabit Ethernet, that gives you about 25 gigabytes per second output. You've got a lot of PCI Express output bandwidth as well. And the latency is very low because the ADCs and the DDCs, the DACs rather, are connected directly to the FPGA fabric because this is a monolithic device. That means one piece of silicon. And so you can have extremely low latency. Typically, we measure at about 50 nanoseconds, which is pretty good. Everybody wants it more, but this is really pretty good. So this really was this product line where we use the RF SoC is the most successful product that our company had ever built in its 35 years of existence. Real winner. But there's more new technology devices available, and I want to share them with you because they're pretty exciting. Last February, Mercury announced the RF SIP, RF System in Package. And what it has is it combines the Xilinx Versal ACAP FPGA, which has AI engines built in, heterogeneous processors, and it has 4 10-bit, 64 gigasample per second A to Ds and D to As, tied to it using multi-chip module technology, 2.5D packaging, which is done right here in Phoenix, in the Phoenix Mercury fabrication facility, which is a DMEA, that's a Defense Microelectronics Assembly fabric, US-based. And the tuning that is available with the ADCs, the DDCs and the digital upconverters gives you instantaneous bandwidth, 4 gigahertz at the outputs, and processing in real time in the FPGA because of the tight connection between the data converters and the FPGA. Now, the way these devices are built is with what's typically called chiplets, which are little I/O blocks, including A to Ds, data converters, and so forth, that can be assembled in these types of packaging facilities into multi-chip modules to give you rather easy connections between something like an FPGA and different types of I/O peripherals using common standard for the interconnect to make it easy to have relatively low, fast, inexpensive new designs created using these assembly fabrication techniques. But AMD Xilinx is not the only one, of course, that's doing FPGAs. There's another company called Altera that was purchased by Intel that's doing other really great and very similar things. Here's another direct RF FPGA, which includes the Agilex, the Altera Agilex family, which is their latest generation, again with 8 10-bit 64 gigasample A to Ds and D to As, using again this chiplet technology and the direct interface to the FPGA between the data converters. Very fast interfaces. There's another device, a Altera Stratix 10AX, which has similar performance. It goes to a sampling rate up again to 64 gigasamples per second, and again, very high-speed input-output interfaces. So what Mercury has done is committed to this direct RF technology, and the first example of it will be the direct RF transceiver called the DRF3182, which is a 3U VPX module that embraces that Stratix 10AX that I talked about on the previous slide, giving you 4 channels of direct input and output, in this case up to frequency bandwidth up to about 18 gigahertz. So from 1 to 18 gigahertz, you can do a wide instantaneous bandwidth, capturing it all, connecting those data samples directly into the FPGA. So this is really a remarkable product, and it's really ready to go. Now, talking about what does 18 gigahertz do for you? Well, this is a chart from IEEE that shows you different things that are going on, and obviously I'm not going to read this, in different bands. You have low frequency, high frequency, the KU bands, the X, C, S, L bands, and so forth. With a 64 gigasample per second A to D converter, capable of handling signals up to 36 gigahertz, you can cover this whole range of different bands that are vitally important to our military. You can see some of the applications that are listed over there to the right. So imagine, now I've got this one data converter that can handle so many different applications, okay? So let's just see how this could be put together in a system. What we're showing here is a 32-channel phased array antenna that's going into a bank of 32 filters and amplifiers, both for transmit and receive, going into RF ADCs and DACs, and then going to a direct connection to the FPGA, right on the same substrate. The output could be optical links using Vita49 protocol to go out down to the rest of a system. So that could go, for example, to a gateway, a resource controller, that could be used to route those signals to different applications, to different consumers of all of that different kind of data that each one of them has a different interest in. So you could have monitoring countermeasures, mission operations, and analysts that are trying to understand critical information, battlefield management. So this concept of sharing one antenna across multiple consumers of different applications required by military platforms is really important to defense everywhere around the world. And that's really, again, the essence and the kind of the final picture, getting right to the edge, digitizing at the edge, connecting, do the initial processing there, and then communicating over extremely wideband links through network connections to all of the different users of that data. I showed you this in the beginning. Just go through what we just talked about. Higher signal bandwidths, got that. Multi-radio acquisitions, we got that. Acquisition at the edge, higher signal complexity with the AI processors, we got that covered. Lower signal latency, those direct connections from the data converters right into the FPGA fabric. Phased array antennas. Heterogeneous computing, like the Versal, for example. And then the stair mode capability, the ability to look at a wide bandwidth all in one look, okay? Really significant benefits. And so I just listed all those benefits here just so you can see them. You can go through them, read them yourselves. But you can see, besides the functional benefits, the system practical benefits of size, weight, power, cabling, and so forth are also huge because they can dramatically change the size, everything about receivers. It kind of revolutionizes the architecture of radios for all military applications. There are some trade-offs. You've got to deal with very fast interfaces if you want to hold all of that wideband data around. And that, again, is what people here have been talking about, is getting faster and faster interconnects in an embedded system, in SOSA, VITA, to be able to handle. So we've got direct RF technology is taking advantage of all of that development, but all of that development will become better, and then that will foster higher performance direct RF applications, and it will just keep growing. So it's a symbiotic relationship between direct RF and all the things that we're doing in VITA and SOSA to support the traffic that it generates. The first devices of any technology are expensive, but the prices will come down. There's going to be more and more competition. There already is competition. And the only other thing I can say is that when you're looking at a broad bandwidth of signal, if you have a strong interferer, you can have a case where it will limit the dynamic range because it's going to overload the A to D converter unless you remove that strong interfering signal. So what you can do is you can put in some very smart and agile tunable filters in the input path in case that you've got a strong interferer. You can notch that out and then look at everything else. So it requires a little bit of design and capability, but one of the things that Mercury has is a lot of different RF solutions to help in the signal chain with things like mimic tunable filters and a lot of RF amplifiers and filters and all of these different components that you'll find will help in the signal chain. And that's why it's really great in joining Mercury. We now have the ability to work with the other divisions that are making all of these other RF components that are critical to defense radio applications. Okay? I think that's it.